Thank you guys for tuning in. Maybe we'll get a couple more stragglers that pop on here. But we are excited to kick off the Thrust B series with the presentation from Dr. Ali Mostafavi at Texas A&M. Using data and models, enhanced process understanding from Thrust A, the impacts of innovative technological solutions on sustainability of water systems across eco-hydrologic regions are examined under Thrust B. These solutions include building to community-scale resource recovery and reuse systems, hybrid centralized, decentralized water infrastructure systems, fit-for-purpose water systems, green infrastructure, sustainable urban drainage networks, and resilient floodplains. The complete Thrust B series schedule is also available on our website. We, like I said, continue to record each webinar and post them to our YouTube channel, and as always, I'll send out a link once those are available. Please be sure to join us next week for a presentation from Drs. Horvath and Stokes-Drought as they discuss life cycle assessment of urban water infrastructure. Okay, so I'm excited to introduce Dr. Ali Mostafavi, Assistant Professor of Civil and Environmental Engineering at Texas A&M University. Dr. Mostafavi's research interests focus on solving the challenges at the interface of the infrastructure system, economy, environment, and society. These problems are often large in scale and multidisciplinary, thereby requiring solution concepts that consider engineering and science simultaneously. His specialties include infrastructure, energy, environment nexus analysis, sustainability and resilience of infrastructure systems, complex system simulation, risk analysis and modeling, financial analysis and modeling, business strategy, innovation assessment, policy analysis, decision-making, and construction management. And with that, I'm going to turn the controls over to Ali. Bear with us for just a moment as we switch screens here.
Okay, thank you so much. And again, welcome everyone. The title of the webinar today is Assessment of Urban Water Infrastructure Resilience, which is one of the research projects under Thrust B of our UWIN network. In this project, overall, what we're looking at is to understand what underlying mechanisms influence urban water infrastructure resilience. And then, based on the understanding of these underlying mechanisms, we're looking into identifying technological, policy, and infrastructure solutions that enhance long-term resiliency of water infrastructure. So, in terms of the project tasks, we are looking into development of solutions and looking at solutions on both the demand and supply side. On the demand side, we look into development of agent-based models to understand the behaviors of water consumers in terms of technology adoption for water conservation. And on the supply side, we look into the dynamics of infrastructure, water infrastructure resilience, especially water distribution networks, and look into their resiliency. Just an overview of our research project. We have looked into development of an agent-based model for modeling the household behavior in terms of adoption of water conservation technologies, established a dynamic model for simulating the performance, long-term performance of water distribution systems, and then looking into dual and singular water distribution systems, especially dual system as innovative infrastructure solution for improving the sustainability and resiliency measures. And finally, we look into conducting scenario analysis to be able to understand under what scenarios, what solutions would be more robust and lead to better resilience performance. So this is an overview of our research project under this trust, but for the purpose of this webinar, I've mainly focused on the second component, which is looking at the dynamic model of water distribution infrastructure, specifically looking at understanding the underlying mechanisms of resiliency using a complex system approach. So the motivation for this study was to understand the long-term resilience of civil systems under different stressors. So as all of us know, the civil infrastructure, including water infrastructure, are exposed to various chronic and acute stressors, including climate change impacts, population growth and decline. In some areas, we have rapid urbanization and population growth. In some areas, we have shrinking cities that deal with population decline. And at the same time, we are dealing with limitations for resources, basically disparity between the supply and demand of resources, including financial resources, and also extreme events. So to deal with these stressors, the concept of resilience was emerged over the past 2 decades to better understand the behaviors of systems under stressors. And basically, there are 2 main paradigms for resilience assessment in the context of infrastructure systems. The first paradigm is an engineering-based approach, which basically looks into how infrastructure systems lose functionality and restore and recover from perturbations caused by stressors. And this approach is mainly used for assessment of resilience under acute stresses such as natural disasters and man-made disruptions. And in this paradigm, resilience is measured based on to what extent a system loses functionality and how fast it recovers. It's a very powerful approach, and it's been used extensively for resilience assessment under acute stressors. There is another paradigm which is called complex system approach, which takes another view into resiliency of infrastructure. So in this approach, the resilience of infrastructure is characterized based on the underlying socio-technical dynamics. So basically, we look into the long-term performance and behaviors of infrastructure. And based on identifying the existence of a steady states of performance and changes in these steady states of performance under different external stressors, and here the focus is more on chronic stressors, we are able to characterize whether these systems have resilience performance. And using a complex system approach, the resilience performance is evaluated based on changes in this stable state of performance, which is being called regime shifts. And the threshold values at which these regime shifts happen are referred to as tipping points. So basically what we do in a complex system approach to resiliency is to understand the existence of stable states of performance, changes in these stable states which are characterized as regime shifts, and also the tipping point values of stressors and system parameters that lead to these changes in the performance regime of infrastructure. So this approach is very effective to be used for long-term resilience assessment, and also capturing some of the important chronic stressors that urban water infrastructure is dealing with, such as population change, limitations of funding, and also climate change impacts. To do this, we established a complex system resilience framework and looked into 3 underlying mechanisms. As I mentioned, one important mechanism in this approach is what are the external stressors, and then how they impact the internal dynamics of infrastructure. And when we look into the internal dynamics, we look into both the physical system and the human system. So basically, we conceptualize urban water infrastructure as complex systems composed of human actors and physical networks. And by looking at the interactions between these 2 systems, we look into how these systems evolve over time under these stressors, and how the internal dynamics of infrastructure systems lead to certain stable states of performance, and how these stable states of performance change over time under different stressors, and whether there are any regime shifts or tipping point behaviors in the system. So looking at the first component, which is external stressors, we look into both chronic and acute stressors. And just for definition's sake, chronic stressors are gradual, low impact, and high probability events. For example, population growth declines. So in some areas, we know that population is growing, and it's almost certain, but the impact is not immediate. It builds up over time. And on the other side, we have acute stressors, which are like abrupt, high-impact events like natural disasters and extreme events. In terms of internal dynamics, we look, as I mentioned, we look into both human actors and physical infrastructure, and we look into how external stressors creates risks and how these risks are perceived by the human actor systems. And in the human actor system, we look into two types of actors: institutional actors and consumer actors. So basically, institutional actors are actors who manage and govern the operation of physical infrastructure, and consumers are receivers of service. So based on the decision-making processes of human actors and institutional actors, the physical networks are renewed and maintained and operated. And based on the performance of physical networks, the service is provided to consumers. On the other way, institutional actors, receive, funding from consumers because of the service that they provide. At the same time, consumers have a demand on physical infrastructure, and physical infrastructure maintenance has an expenditure on institutional actors. So this figure, to some extent, captures the internal dynamics of physical infrastructure and human actors, and how different stressors can lead to changes in these internal dynamics. After we understand the internal dynamics in the complex system resilience approach, we look into evaluating resilience performance. As I mentioned, two important concepts in assessment of resilience using complex system approach is regime shifts and tipping points. And regime shifts are changes in the stable states of performance over time. And the concept was originated from ecological sciences, and we adopted it for better explaining the changes in the long-term performance of infrastructure for resilience examination. And the second concept is tipping point, which describes the threshold values of external stressors or values related to internal dynamics that lead to changes in the performance regime of the infrastructure system. So based on understanding regime shift and tipping point behaviors, we try to understand the long-term resilience performance of infrastructure, as I will explain in more detail talking about our case study. So we adopted this complex system framework in a case study of City of Miami Beach water distribution pipeline, which is composed of 180 miles of pipe. So the network has different types of pipes. We collected the data about the length of pipes, different material, age categories, and also the population of the service area to get a sense of the level of demand and other measures that we needed to implement our complex system framework. Then we use the data and the framework to implement a multi-agent simulation model. So in our multi-agent simulation model, we have three classes of agents, including the pipeline network, utility agency, and water users. And the main functions in each of these networks are shown on this slide. So for pipe network, we are looking at the physical deterioration of the network. For the utility agency, we are looking at the renewal decision-making processes, and for water users, we are looking at the changes in the population and level of demand for water. Looking at the first agent, we tried to model the physical deterioration and degradation of physical networks. What we did was we looked into the entire network and classified the pipes in the network into different categories, or what we call age conditions, based on the age of the network, which is a representation of the condition. So we have 5 age categories: condition group 20, 40, 60, 80, and 100, which basically represents the age and condition of each set of pipelines. And also under each age category, we determine the percentage of pipes which are of different materials. In this case, the two types of materials are PVC and CIP. And as network ages, pipes flow from age category to the other. And another mechanism that changes the flow of and degradation of the network is renewal, which is basically governed by the decision-making behaviors of the agency. So depending on the availability of funding and the priorities of the agency, certain percentage of pipes get renewed each year, which brings the pipes at from the highest age category to the lowest age category, which is 20. So we use different measures for capturing the network level performance. For example, one measure that we use is the average condition of the network, which is basically a weighted average of the age of the network based on the percentage of pipes that are in each age category. We also use other measures such as the network breakage, water leakage, and service reliability, which is based on the percentage of time that the system is able to meet the 100% of the demand. Then the second class of agent in our model was the institutional agency, and the main function for that agency is implementing renewal decision-making processes. So there are different factors that affect the renewal decision-making processes, including the water demand and water price, which determine the revenue that agency receives, and based on the availability of funding and the condition of the pipes, the agency determines the percentage of the pipes that can be renewed each year, and depending on the renewal strategy, the pipes are prioritized for renewal. So in this study, based on the literature review, we identified three main strategies. One is regular renewal, which is renewal of certain percentages of pipes, let's say 5%, 6% each year. One strategy is based on break frequency control, which is maintaining the break frequency at a certain threshold. For example, if the agency wants to limit the number of total breaks each year to a certain level, that would be a break frequency, and if they exceed that, they invest more in the renewal of pipes. And then the third strategy is the average condition control, which is maintaining the overall network condition at a specific condition level, which is based on age. Let's say 45 or 40, the agency prioritizes the renewal decision making. So the figure on the right hand side shows the renewal decision making process for maintaining the network average conditions. So based on the threshold that the agency defines for the target for average condition, the availability of funding, certain percentage of pipes in the network get renewed, and if the funding is not available, the renewal would be just governed based on the availability of funding. So the outcome of this decision-making process determines the renewal process that I showed in the previous slide here, that brings the pipes from older condition to age condition 20, which helps in modeling the degradation and renewal process in the system. Okay, so here we have the output interface of the model. So before showing that, I would like to show the animation of the model. So our simulation model has a user interface which captures three sets of information related to city, network, and agency. So at the city part, a user can define the number of households in the city, the population of the city, the population rate, which is growth or decline, and also the energy intensity of water, which is basically based on the information about the treatment processes and pumping, etc. At the network parameter part, the characteristics of the network are defined in terms of the distribution of pipes at the beginning of the analysis into different age categories, and also the percentage of pipes in each age category for different materials. And the other parameters include the average pressure, average flow rate, and average failure duration in case there is a break. And in the third component, which is agency attribute, the strategy for renewal is determined. So we have three renewal strategies, as I mentioned. Then the threshold for each of those strategies are determined, and also the water price and water price hike and possible capital improvement budgets, which are in addition to the revenue that the agency has, which are usually capital improvement programs that lead to major renewals and improvements in the network. So after a user defines these input parameters, they can run the model, and the user output interface is appeared. So on the output interface, we have on the top part the different edge categories and the gradation of the network to see how different pipes move from one edge category to other edge category. And at the bottom, we have different charts that simulate the network level average condition, amount of network leakage, then annual energy loss, number of breaks, and level of service. So in this outputs, the measures related to average condition, leakage, and energy loss are deterministic, but the one related to annual breakage is stochastic because we use the stochastic process to simulate the breakages in the networks based on historical data of pipe breakages. So we use these outputs to determine the existence of certain performance regimes and the different trends in the water system performance under different scenarios. So this could be used for us to identify the two phenomena that we are interested, the existence of regime shifts and also the tipping point behaviors in the system. So we did that and we used the model for scenario analysis, but before we started the scenario analysis, we tested the model through different verification and validation techniques. We adopted internal verification to make sure that the logics in the model are properly built. The model creates consistent results, and then we use data model verification to ensure the quality of the model in terms of completeness and consistency. And then, we used other validation techniques to evaluate whether the trends and behaviors that are observed in the system are reliable. So accordingly, we designed our simulation experiments. The powerful aspect of using simulation for evaluation of resilience behaviors is that we can simulate multiple scenarios. So unlike historical data that we just have certain possibilities out of many possibilities that could happen, simulation enables us to expose the system to different conditions and stressors on the different scenarios and evaluate how these changes in external stressors and parameters of internal dynamics lead to certain behaviors. So as you can see in this table, we have scenarios related to different population change rates, water price changes, levels of capital improvement, agency renewal strategy, and desired performance thresholds for different strategies. So in terms of the results, we show some examples of the results that we got from this analysis. This specific sets of results include the network average condition under different scenarios of capital improvement funding, from $10 million to $30 million, and also different strategies, including average condition, strategy, and break control with different thresholds. So looking at this, what we were interested in is to identify the existence of different stable states of performance. So if you look into the scenario related to $10 million capital funding, we can see that under different renewal strategies, we have a similar performance regime. In terms of shape, in terms of trends, they are similar. However, if we change the threshold for break control in the last scenario, we can see the performance regime of the system will change. So this is an interesting phenomena which implies the changes in the performance regime of the system. So we can look into that from another aspect as well. So for example, for a specific for a specific renewal strategy, let's say average condition with a threshold of 45, we can see that if we have $10 million of available funding, we have a specific performance regime, but we increase it to $15 million, the performance regime will change, and it stays the same with the higher levels of funding. So there are a couple of interesting observations here. One is that these parameters shown here are parameters related to the internal dynamics of the system. So this shows that the internal dynamics of the system shapes the performance regime of infrastructure. And another interesting observation is that changes in these parameters will change the performance regime. So we can look into this complex system approach and the phenomena of regime shifts to better understand resiliency, which has not been characterized before. So here we characterize, for example, that for this system with this specific physical conditions, there is a tipping point behavior at $15 million that changes the performance of regime of the system under average condition 45, which implies that for this system, we need $50 million capital improvement program every 5 years to maintain the network condition in a better level of average condition. If we have less, the system will perform under a completely different performance regime. But if we have more, there is no major difference. So basically, spending more on the system will significantly improve the performance of the system. So that's an interesting aspect. So basically, for each system, for each water infrastructure network, there is an emergent level of funding which is required to maintain a system at a certain performance regime, which is to have a resilient performance. Another set of findings that we have is related to the sensitivity of our system performance to external stressors. So we looked into two external stressors. One was population change, the figure at the bottom, and the other one is capital improvement funding, the figure at the top. So if you can first look into the one at the bottom, you can see that if we don't have any price change in the network, if the agency decides not to change the price during the analysis horizon of 100 years, which is our a duration for this analysis, the system becomes very sensitive to population change. Even 1% change in the population will lead to significant drop in the level of service reliability of the system. However, this sensitivity diminishes if the agency adopts, let's say, 4% or more water price hike. So basically, for this specific network that we analyzed, there is a need for 4% price hike every year, so that the system becomes less sensitive to changes in the population, which is another interesting finding related to establishing the threshold values for tipping points in the behavior of the system. Looking at the figure at the top, we see the different levels of capital improvement funds and the service reliability under different renewal strategies. So two interesting observations here include the different behaviors under network average age control and network breakage control. We can see the system behaves differently under different strategies, and then the sensitivity of the system performance in terms of service reliability is different for different strategies. So when we have average break frequency control, if the funding changes, the service reliability does not change significantly. However, if we are looking at controlling the network average age, then the system reliability becomes very sensitive to capital improvement. And there is a specific capital improvement, as we saw in the previous slide, for this network around between $15 to $20 million, beyond which the performance of the system does not improve. So basically, what we can understand from these results, from theoretical aspect, is to basically we can characterize resilience performance based on the existence and patterns of behaviors related to regime shifts and tipping points. And from a practical perspective, we can look into what is the appropriate level of funding to improve the resilience performance of this system, and how we can reduce the sensitivity of these systems to different chronic stressors over time. Okay, so that was the first part of the study that we did, which is the establishment of the framework and development of the model. Then we realized that, okay, it's not just scenario analysis. We can use the simulation to test different solution concepts. One of the solution concepts that we are looking at is, looking at dual distribution systems as one innovative infrastructure solutions. Basically, the existing literature shows that dual systems can potentially decrease treatment energy usage, decrease operation and replacement costs, and reduce water age. So basically, they can potentially improve the performance of the network. So the question for us is, whether dual systems can also improve the resilience performance of the networks over long term under different stressors, and we use this model that I explained in the first part to do this analysis. So this work was implemented using the data related to city of Fort Collins, and we collected data related to water distribution system in city of Fort Collins, and looked at the previous study that was done to establish some characteristics of dual distribution systems. And we used the data to recalibrate our simulation model and make required modifications to capture the characteristics of dual systems and conduct scenario analysis to evaluate, the long-term performance of the system under each of these scenarios, and also for different systems, dual versus singular systems, and evaluate whether actually dual systems would perform better or worse under different scenarios. So our analysis is ongoing. So some of the preliminary results that we have is related to looking at different network performance measures, and some of the preliminary results that we have, these are as I said, preliminary results. We are verifying them, and it's an ongoing activity. But some of our preliminary observations suggest that dual systems can lead to almost 50% less energy loss rate in the systems over a long term. And also under a specific renewal strategy, let's say regular renewal, dual system can have about 9 to 10% better condition over time. And if you look into other measures, let's say total breakage, we can see that the breaks, total breaks per mile are less in dual systems compared to singular systems. So this is promising in terms of being able to quantitatively evaluate the performance of these systems under different scenarios. And currently we are looking into scenario analysis because we believe that there might not be a one-size-fits-all solution. Maybe we have dual systems more appropriate for certain scenarios, and singular systems more appropriate for other sets of scenarios. So currently we are looking into those issues to be able to establish under what scenarios these systems would be more resilient, and report those findings hopefully in future webinars. So just to summarize, in terms of the work that we have done so far, in terms of theoretical contributions, we have established a complex system-based framework for resilience assessment in infrastructure, and we applied it in the context of water distribution infrastructure, and developed a computational model using a multi-agent simulation approach to capture the internal dynamics of infrastructure and human actor decision-making to be able to simulate long-term performance and transformation of these systems under stressors. And from practical perspectives, the findings that they have come up with so far help us identify the infrastructure and policy solutions and operational strategies that could lead to better and more resilient water systems and different areas. So in terms of the next steps, we are, as I said, we are comparing different infrastructure solutions, and we are trying to look into different UV cities and try to see that whether the characteristics of each city will affect the long-term resilience performance, and also whether each sets of solutions and strategies would be more specific to a specific geographic and regional setting, and we go towards a more flexible strategy development rather than having, as I said, one-size-fits-all solution concept. So with that, I would like to close the presentation and answer the question. But before that, I acknowledge, the PhD student on this project, Cont'd Rasul Khani, who everything that I presented was his work. I just, did the presentation. So all the credit goes to Cont'd. Okay, so I guess, we need to answer the questions.
Yeah, sorry, it took me a minute to unmute myself. Thank you so much to both you and Cambiz. It was a wonderful presentation. Jen has a question. She is wondering, for your preliminary results of dual versus singular systems, how applicable are these results to other utilities?
Okay, that's a great question, Jen. So basically, for the city of Fort Collins, we had the prior study that looked at the characteristics of a dual system and singular system for the city. So, in the previous studies, Sybil and Jeannie developed a EPA net model of these two systems. So we have the system specifications in terms of the system pressure and the average flow rate, etc. The parameters that we have in our system. So if we want to apply them into other contexts, I think what will change is in terms of the network, attributes is the length of the network and also the age of the network. So this, if you have a network which is, in a better shape, maybe this will affect the feasibility or plausibility of dual systems. But if you have an aged network, aged singular network, maybe the dual, network becomes more plausible. And on the other hand, it depends on the trajectories for population growth, the level of demand, and water price, because what we observed is the allocation of funds between these two systems. So we have a system, singular system, which is for non-potable water. I mean, singular system delivers both potable and non-potable water. So you have just one price for water, but for dual system you have different price ranges. So demand fluctuations for each of those systems will affect the ability to maintain those systems, because the cost of maintenance renewal is potentially going up because we have more a longer length of pipes to maintain. So that's a really good question to look into other settings and see that whether the plausibility of these systems would be sensitive or contingent on the characteristics of the physical systems and also attributes of the other utilities. Not sure if I answered your question.
Thank you. We'll see if Jen fires back. And I should add, I didn't announce this at the beginning, but if you have any questions, you can enter them in the question or chat queue. That's where these are coming through. We will hopefully get a copy of Ali's slides. If you want to put those on the ERAMS user group that we made, that would be lovely for folks that kind of jumped in late. I have a couple of requests for slides. Ali, if you could do that.
Sure, absolutely. I send it along right after this webinar. And I see there is a question from Sybil, right?
Yes. She said, could sensitivity analyses help to assess applicability to other cities?
Oh, absolutely. So that's definitely one important component of the analysis, because sensitivity analysis determines the extent and magnitude of external stressors. For example, changes in the availability of funding, or change in the water price, or change in the demand. So those are the model input parameters that we define, and also changing the network age and the distribution and material types will also change the performance. So definitely, one aspect of looking at the applicability to other cities is to look into sensitivity analysis, and then we can see that, okay, if cities with these characteristics, with higher demand and greater projections of population growth, they will have more benefit to gain from dual distribution systems, let's say, compared to other cities. Again, what I say is hypothetical, but this is the type of observations and results that we expect from this analysis.
Great. So another question is, what modeling tool was the first model displayed built in?
Okay, so the modeling approach, as I mentioned, is multi-agent simulation modeling, and the tool is called AnyLogic, which is a simulation modeling platform, which is basically a Java-based platform for developing object-oriented models, including system dynamic models, discrete event models, and also agent-based models. So we use AnyLogic for developing the multi-agent system model of water distribution.
Great, thank you. Well, I will take this opportunity not only to, again, thank Ali and Kambiz for that great presentation. Always good to get a higher level of detail with our various UN projects, since there's so many. I would also like to add that, our annual meeting is quickly approaching, so if you have not already done so, please register. Registration is closing on July 1st, as I have a bunch of final headcounts due. And also, MASDAC just sent out an email about a half an hour ago to announce that we are actually doing student poster awards this year, and each award is for $1,500. So if you have students that were waffling on if they want to come, that might be some good incentive for them to put together a poster. So feel free to forward that along and contact us with any questions. Looks like our questions have all been answered at this point. Do you have any closing remarks, Ali?
No, thank you so much for the opportunity. If you have any follow-up questions, feel free to contact Kambiz or myself directly by email.
Wonderful. Great. Well, we'll send out a link once I get it posted to our YouTube channel, and we look forward to seeing everybody in person in a couple weeks. So have a wonderful afternoon, everyone. Thanks for tuning in today.
Thank you.
Take care.